Let's talk about Gauss's law. I've mentioned it a few times already, and I really didn't learn it as well as I should have when I first took physics. But in hindsight, I really should have, and it's not that bad. So you're going to see an equation for Gauss's law, probably something along these lines. So you have Q enclosed over epsilon naught equals double integral circle thingy, and then let's see here, probably an electric field dot dA. So a little discussion about what this means. So kind of to mitigate expectations, I'm not going to derive this, partly because you don't need it for the AP test, and partly because I am not familiar enough with vector calculus to really do it justice. I'm just going to talk about it and how it's applied for the AP test. So first, going through the equation, talking about what it even means. So a lot of times you'll just see Q here. Q enclosed means what we're going to do is we're going to draw some, what they call like a Gaussian shape. And within that shape will be an enclosed charge or no enclosed charge, which in case if there is no enclosed charge, that would mean there's no electric field. So you might think, how do we choose the shape? We'll get to that. So choose the shape, and then the shape will give us what the enclosed charge is. Epsilon naught, I don't think you've seen epsilon naught, but you kind of sort of have, because when we use K, K is also equal to 1 over 4 pi epsilon naught. And K is a Coulomb's constant. I think K is a Coulomb's constant. Maybe epsilon naught is. I should know that. It's okay. Not important. So remember when we had Coulomb's law, we had force electric equals K Q1 Q2 over R squared. This K right there was 1 over 4 pi epsilon naught. And your thought process might be, why do they just have such a simple change in symbols? Well, they're adding complexity without reason. It's just science with more steps. Probably true. That's kind of what I've come across. I assume there are historical reasons why they've always kind of used K for one thing, epsilon naught for another. And if you're the sort of person that does these on a daily basis, you get tired of writing 1 over 4 pi epsilon naught and appreciate writing K. That's just my guess. If I could rewrite science, man, that'd be terrible. But if I could, I'd just get rid of K or epsilon naught. But, one or the other, but not both. So then we have a double integral here. We have a double integral because we have a differential with respect to area. Sometimes you'll see a single integral, but I like to think of, and it's not necessarily xy coordinates, but that's the dimensions I'm going to use for this. I like to think of area as change in one direction and a change in another direction, measured mostly in meters. That looks like a W. I meant M. And so you're going to integrate in one direction, and then you integrate in the other direction. And your first thought is, I don't want to do double integrals. And what's this little symbol in the middle? That circle thing. Well, the circle means it's a closed surface. And I'm just going to say right now that don't worry too much. We will make sure to choose the electric field in such a way, or the shape in such a way, that you almost never have to do this integral. The only integrals you'll really have to do will probably be for Q enclosed, because you're trying to integrate given a density, charge density over a shape. So the integrals you'll do will be fairly simple. And when I was talking about the shape earlier, not our entire goal, but the vast majority of our goal for choosing our shape will be so that the shape, I'm going to make it a cylinder? Yes. Cylinder like this. So the idea here will be you'll want the electric field to be parallel or perpendicular with the That's not a good example. Perpendicular. You want the electric field to be either parallel or perpendicular to the area at all places. Probably easier to do a sphere. Already leading you astray. You have a shape. You have a positive charge going outward. And so what you have here, you have an electric field going outward. And then you also have the area going outward as well. And so what happens, and since this is a dot product between the two, the magnitude of a dot product is, what is it, cosine? Cosine. So cosine of theta, in this case theta would be 0, therefore there won't be, it will just be 1. It'll be, the magnitude will be the magnitude of electric field times the magnitude of the area times 1. And since the electric field will be uniform with respect to where we're measuring it at the area, we'll be able to almost always pull that E out. And then this means that it is a closed surface. So at this point, it's going to be easier for me to just do an example to kind of show you how this works. Now, Gauss's law, we only use Gauss's law usually in like 4 or 5 or 6 different circumstances, and most of it is to derive formulas that we're going to probably memorize anyway. So the way I was able to get away with not learning this and just kind of winging it, we're just memorizing the end results of some of the applications of Gauss's law. I do not recommend doing that. I made a lot of mistakes in my life, and you're better off in life if you learn from other people's mistakes instead of your own. A lot simpler, a lot smoother road. Okay, so we're going to say, as an example, that we have a Control C. Oh, what's going on? No, what are you doing? Go away. Outrageous. There we go. Oop. So we have a charged particle, and it's going to have positive charge. So I'll have charges going outward. You're like, is he going to draw 8 of them? So tedious. So yes, I know. There's not a whole lot of value added by drawing 8 versus 4, but I personally enjoy it. It makes me feel warm and fuzzy inside. All right, so this is a sphere, and we're going to apply Gauss's law. So first thing we're going to do is we're going to choose a shape. And like, well, what sort of shape are we going to choose? A red one. Oh no, I don't want. There we go. Orange. We want to choose a shape so that the dot product, electric field dot dA, is either perpendicular or parallel. Parallel, cosine of 0 will be 1. Perpendicular, cosine of 90, or pi over 2, or cosine of perpendicular, is 0. Therefore, it can be ignored. Anything else requires extra calculations and difficulty and wants to be avoided, especially on a time test where your free response questions get like 15 minutes. You don't have time to do anything complicated. And most of those free response questions, they have like 5 parts. So really, you get like 3 minutes per question. Okay, so first thing we're going to do is we're going to write down Gauss's law. So Q enclosed over epsilon naught equals double integral of E dot dA. These are both vectors. And so the vectors, when we dot plot vectors, you get a scalar, which makes sense because then we have a scalar on the left side. So the formula at least seems to be reasonable at this point. So first thing we're going to look at is Q enclosed. I'm going to say that this is just Q positive. We have a Q enclosed, Q positive. So it's given. And we're trying to find the electric field. Change colors to represent our change in train of thought. Okay. So then we want to look at the electric field. I'm going to zoom in right at this point. So we zoom in at this point. Draw kind of a square, kind of flat. So we zoom in and kind of turn it sideways. And so what I'm trying to show here, albeit not the best, my artistic skills are lacking. Now these are supposed to be right on top of each other, but it'd be hard to see that way, so I'm drawing them next to each other. So this is representation of the surface of this sphere, this Gaussian sphere. And we're approximating it as flat. This is the same idea as you walk outside, you look around, you're like, wow, this world thing seems pretty flat. Those flat world people, flat earthers, they sure got a point here. And the idea is that when you zoom in far enough, most things can be approximated as flat. I think that's the definition of a manifold. I should look that up. So the idea is spheres are approximately flat when you zoom in enough. And the dA vector, so the area vector for a surface, is the vector perpendicular to that that surface. So the idea is you have a plane, takes up 2 dimensions. So you're like, well, here's the third dimension with respect to that plane, and that third dimension is in no way part of, I guess, except for that one point, that plane. And that's how you define it. It's basically with the you can define planes by their perpendicular. And so that's what we're doing here. And then the electric field, it's radially outward. So in this case, it'll be the same direction. So what we're going to do then is we're going to, since we chose the sphere, think how much harder this would be if we had chosen like a cylinder. Because if we'd chosen a cylinder like this, then sure, straight out this way would be the same. But then we'd start having all these crazy angles and then be a huge mess. Huge mess. The entire goal of choosing a Gaussian sphere is avoiding crazy angles. And that's why these Gauss's all work for a lot of things, but there's a lot of things that just won't work for too. They're usually pretty obvious which ones to work for. Generally, the shapes you'll choose will be a cylinder, a sphere, maybe a cube, but that's about it. Okay, back, focus, back on track. Ooh, green. So looking at our equation, the electric field at every point will be the same because the electric field will be going outwards and it'll be at the same radius for all of them. One of the ways you can interpret a electric field, let's see here. How can I justify? So one way you can look at electric field is when you draw electric field lines, the separation, the density of the arrows will represent this magnitude of electric field. And you can see at every point the electric field will be perpendicular to the Gaussian shape. Now I know this isn't really a rigorous proof, but I'm trying to convince you reasonably, and this is kind of not a shaky proof, but there's a lot of formalities that I'm skipping, that the electric field at every point of this sphere will be the same. And so if something is a constant, you can pull it out of the integral. So if you have 2 times the integral of x squared, or integral of 2x squared is the same as 2 times the integral of x squared. So we can pull out the electric field. We're going to get rid of the vector lines at this point. It's going to move it back to its magnitude because we already know that the dot product will be 1 at every point because the electric field is parallel. So I probably shouldn't have that dot there. Ignore that dot. I'll try and, oh, it's terrible. Integral of dA. So now we look at this. So this side here is what we're looking for, and we can find out what this integral is because that is just the surface area of a sphere, which is, as we should know, 4 pi r squared. You just have to memorize that. Sorry, you should know it already. If you don't know it already, you should learn it. When Q, C-U-E, in life, that this is maybe possibly correct, is this is r squared. Whereas if this was r cubed, you'd be like, that's probably a volume. That's probably a volume. This is not a volume. This is a surface area. So that's when, not really showing that you're correct, but it's at least showing that you're not completely wrong. Okay. So then we're going to solve this for E. E, electric field, equals, since we know this is 4 pi r squared, that's Q enclosed, then we'll have Q enclosed over 4 pi epsilon naught r squared? 4 pi. Yep. Epsilon r squared equals electric field, which we know, I'm going to make it a little arrow, not an equal sign. So we know earlier from Coulomb's law, that electric field equals K over Q over 4 pi r squared. Where, make a little 1 there. That's the K, Q over 4 pi r squared. And that is how you can use Gauss's law to prove Coulomb's law. And then I'm going to throw in a little vector here just to show that it's in the radial direction. A little hat. Show that it's a unit vector. It just gives us direction, but without affecting the magnitude. Okay. Anything? Okay. So a couple of interesting points here that I should dwell on. So if we change the question slightly, and this is our uniformly charged surface, and we have positive charges throughout. And let's say it's an insulator so that the charges are not allowed to roam freely. These are not free-range charges. And our goal then was to find the electric field at R. So E of R, where little r is less than big R. And so what we do then is we use Gauss's law. Or you take the shortcut and just be like, yeah, it's probably this answer, which you'd probably be right. So we would do Q enclosed over epsilon naught equals double integral E dot dA. Handwriting is atrocious. Now this time, since it's, now we might be told that the Q plus is the total charge. And so Q enclosed is not Q plus. So Q enclosed would just equal the fraction of the total sphere. So we'd have 4/3 pi r cubed. 4/3 pi r cubed is the volume of a sphere. Is it the volume of a sphere? I should check this out. So to verify, geometry, skills, activate. Cylinder sphere, 4/3 pi r cubed. Okay, so we're good on that one. So yes, 4/3 pi r cubed. Over 4/3 pi big R cubed. And you see that this cancels, that cancels, that cancels, this cancels, and you're left with R over R cubed times whatever the big Q is. And so, let's see here. Yes. I'm agreeing with this so far. Okay. We'll pull the E out, the electric field, and so I'm going to say it equals electric field double integral dA, where the area we know is 4 pi r squared, little r squared, because our Gaussian sphere is actually inside of our big insulator sphere. And so then writing everything out, we will have r over big R, I'll redistribute that, times Q plus, and I'll put an epsilon naught on the bottom, equals, and just writing this, substituting that in, over times electric field. I really shouldn't have that. There we go. Electric field times 4 pi r squared, 4 pi r squared, where r squared is specifically the lesser r. And those cancel over there, and we're left with the electric field. And this time I'm actually going to put a vector symbol on it. So we'll have Q plus over 4 pi epsilon naught, so 4 pi epsilon naught times r over r cubed. And we'll do a little r hat for the direction vector. Okay, so it looks like we got a completely different formula this time. And it's good to understand what happened. So what this is saying is, as the radius, little r, gets bigger and approaches big R, then what's going to happen is we're going to pick up more and more charges. There's going to be more enclosed charges. But if we're choosing a small area in the middle, then we're going to have to account for some of the charges on the outside in this area right there that aren't getting counted towards this Q enclosed. And one way to kind of test this to be like, well, does this make sense? Is we know how to find if big R, we know find the electric field if little r equals big R, because that would just be Coulomb's law. So we said, well, if R equals R question mark, then we have Q over 4 pi epsilon naught, which is the same as K, R over R cubed in the R direction. One of these cancels, and we're left with K Q over R squared, which is what we're used to. So it's like, okay, this kind of sort of almost makes sense. So that is how you use Gauss's law for a sphere. Okay, does that seem reasonable? We're going to go into a couple more examples. So there's a few times that you will, oh, one other thing, almost forgot, would have been disastrous. So one last thing with a sphere. Let's say instead of having an insulator, this time we have a conductor. So we have a conductor, all the charges are going to be on the outside, because the charges want to get as a solid spherical conductor. This is just a metal ball, if you will. Let's say we want to find the electric field at some r less than r. For the same scenario here, we have r, little r, big R. This time, Q enclosed would equal 0, because all the charges would be on the outside of the conductor, not the inside. Therefore, the electric field inside the conductor would be 0, which we kind of already knew. We stated that about 1 billion times when we talked about conductors, is that the electric field inside a conductor is 0. And knowing that the charges go to the outside and then applying Gauss's law, this makes sense. So it's like, okay, well, maybe it doesn't make sense, but at least it's consistent, which is all you can really ask for in physics anyway. So conducting sphere, no electric field inside your conducting sphere. Okay, that's enough of those spheres. Down with you, spheres. We're done with you. Now, let's go on to infinite slabs or planes. Do we want to do an infinite slab? Yes. We want to do an infinite plane. Ooh, can I do like a parallelogram? Maybe I'll get some. Ooh. This is going to be more trouble than it's worth, but I'm going to do it anyway. Anything for slightly mediocre artistic abilities. Oh, infinite plane. Don't mess it up. Yeah, surprisingly adequate. Okay, so we have an infinite plane. You're like, wow, that doesn't look infinite. That just looks large. Yeah, it's close enough to infinite. And that's one of the key words you kind of want to look for on tests and questions too. When a test says a large plane or a large whatever, what they're saying is approximate as infinite. That way you don't get like the idea of like, wow, this is towards the end. Things get kind of fuzzy. Yeah, okay. We're good with that. Okay. So we want to find the electric field at some point here. Draw a little line. Electric field equals question mark. And this is let's call this an insulator. And it has a charge density of rho. And I'll put a little Q down here so we know it's an electrical charge density. Is that all information we need? Yep. I will assume infinite large. I won't write that down, but this is assumed. And yep. So now we're going to use Gauss's law. So as general in life, you read a problem, first thing you do is draw a picture. It doesn't really have to be a good picture, but it kind of centers your thoughts. In this case, I kind of drew it for you. But if I didn't, you should draw it. And then we'll do Gauss's law. So we'll do Q enclosed over epsilon naught equals double integral. Sometimes you'll see it as a single integral. I prefer it written as a double. And I would like to draw these vectors for specifically when I first draw it out, because that helps me remind me that these are vectors and the angles are important. Specifically, we want them to be perpendicular or parallel to each other. Okay, so now we need to choose our Gaussian shape. Gaussian. So what we're going to choose is a cylinder that goes through the plane. I know my artistic abilities are failing me here, but the idea here is draw little dots. Should I draw dots down here too? Oh, now I'm making it too complicated. So we have a cylinder that goes through the plane. As I did, and I kind of discussed earlier, that it's reasonable to assume that the electric field is going to be going straight up out of the plane. And the reason for that is, if you look at this as a whole bunch of point charges, they'll be going in all sorts of directions, but it'll work out just fine that this electric field going this way cancels with this one going that way cancels with that one, this one with that one. The idea is everything except the straight ups will cancel with each other. And so we didn't discuss how strong the electric field would be, but we discussed that it would be straight up. And so now we're trying to find the magnitude of this electric field. So now that we know that the electric field is going to be straight up, we're going to draw it like this. This will be electric field. I'm going to draw the area. So dA vector is going to go up so that the electric field going up and this one is going parallel. Now if you look at the bottom side, since this is a closed shape, the Gaussian shapes are closed. The area for this one is going to be pointing downward, but using the same logic as before with the upside, we can say with the downside, where the electric field is going straight down. So, okay. Let's look at this. So I'm only going to focus on the top, and then at the end I'll be like, well, and then we can say the same for the bottom. So, let's see here. Electric field. Maybe. Yes. Okay, so let's start figuring out. We know what, I'm going to start with epsilon naught. We know that. It's a constant. Check. Awesome. Q enclosed. Do I want to do that? Okay, let's do Q enclosed. So the way I like to look at Q enclosed, so what we're given here is rho, which is a small unit of charge for a small unit of volume. I'm never quite sure how to write volume, because do I use a big V? Do I use a small v? If I use a big V, then it looks like potential, which we haven't talked about yet, but we will. And if I use a small v, then it's like, well, then that's velocity or specific volume. So I just write a big V normally, but yeah, it does kind of get confusing. And so, and just a small warning here, my notation is atrocious, but I like it. And I would focus more on understanding what's going on, and then if you're writing some sort of formal paper, you can clean it up, but not really necessary for problem solving, usually. So I'm going to separate this out as, so the definition of electric charge density is a small unit of charge for a small unit of volume. You will also see things such as sigma, which is, and I'll write a little Q here, which is a surface charge density. So it'd be a small unit of charge for a small unit of area. And then you also see lambda for a linear charge density of delta Q, small unit of charge for a small unit of length. So what I remember is lambda starts with L, sounds similar to length. So that I use that mnemonic, that L, length, and that's how I keep those together. For sigma, sigma has a lot of area in the middle, because it's basically like an O with a little hat on it. And that lots of area reminds me that, okay, this is going to be a area density. So delta Q over delta area. And then I'm like, well, rho is the last one, so rho, which you've probably already seen rho used as density, mass divided by volume. Well, this we're just going to use, instead of mass, we're going to use charge. This is a volumetric charge density. Okay. Tangent over, circle back. So now I'm going to multiply delta V by the other side. And we're going to have rho, I'll write the little Q down there just so we remember, delta V, integral. So I write it, separate them out, and then I take the integral of both sides. And the integral of the, and let's see here. So I'm usually kind of vague with where these integrals go from. I am sort of vague. You could say that it's from the top of the shape to the bottom, top of the plane to the bottom of the plane. You say it's top of the shape, Gaussian shape, to the bottom of the Gaussian shape. It doesn't really matter, because I'm basically going to take it over the entire, I guess, interval. So I'm going to say top of the plane to the bottom of the plane, but what that's really going to give us is all the Q enclosed of the plane we're looking at. So it's the Q enclosed within our Gaussian sphere. So take the integral over everything. I know, bear with me here. So we're given that the charge density is constant. A lot of times it's constant, not always, but most of the time it is constant. And so since it's constant, we can pull that out. So we have Q enclosed, then we have integral delta V, which equals, and then this is going to be the volume of our plane within our Gaussian shape. You could, if you also wanted to, you could break this up into two parts. So where this is rho Q times delta V, where this is not in the plane. So you could find the charge density that's not in the plane, basically that area above the plane, but that'd be zero because there's no plane involved. So then this whole section would go to zero. So if you feel uncomfortable, you can kind of look at it that way as well. Don't overthink it. Okay. So then here we're going to have rho times rho charge times the volume of our Gaussian shape that encloses the plane. So right here. And that's just going to be a small cylinder. small cylinder that intersects the plane. So the volume of the cylinder will be pi r squared, because that's the area of the circle on top, times whatever height of the plane is. Call this h. Okay, so what I'm going to justify is that Q enclosed equals density times pi r squared h. Now, some of you people out there that are a little bit more clever in life, which probably many of you, would probably think that, well, you're always taught that density equals mass over volume. So we could kind of say that when we have this charge, it's probably just charge over volume. And so charge equals rho times volume. And that's pretty much all we did. I did it in a slightly more formal, though still terrible, because see, I got this delta and the integral. Shoddy. I like my way of doing it for a lot of these problems, because if you don't have a constant rho, it makes things a little bit more obvious about where to diverge from this methodology. But you're right. You probably could just say Q enclosed equals density times volume, which is in the end all we really did anyway. Okay. Circling back. So now we got one part, Q enclosed. You're like, wow, if that Q enclosed was this hard, how much harder is the rest of the problem going to be? That was the hardest part. I tend to do the hard parts first, because then it's all downhill. Start off with a hard part in life, and then you have easy street after that. Okay? We determined that electric field is constant, so that's just going to be pulled out. And so what we're going to be looking for, let's see, electric field, double integral, E dot dA, nope, dot dA. And so now what we want to do is we want to find the surface area of our Gaussian shape. So before, when we did the volume, we only looked at the part intersecting the plane. Now we want to look at the part for the entire Gaussian shape, which is a little bit different. So we want the electric field at this point here, and that's how you would use the Gauss's law to find the electric field at different points, up versus down. So we're going to call this R. Do we want to use one R or two R's? So I'm going to say that R is the distance from the center of the plane to the top of the Gaussian shape that we have, our imaginary Gaussian shape. So the question is then, how do we find this area? So we actually kind of have to break this up into two parts. It was unfair for me to pull this out for this E, so I'm going to go back and address that a little bit more. This yellow is not a fun color. I'm going to head back to blue. So we should really break this up into two parts. So we have, the electric field, looking at the top, so this is going to be this part right here. This, we have dA going up, and we have electric field going up. And so we can, those will equal, the dot product between the two will equal 1 times E times A. So this will then give us electric field dA, or not, electric field times the integral, surface integral, dA. We also then have another part where we're looking at the sides of, I'm going to draw little dots here to show that this is not the top of the Gaussian shape, but just a side of the cylinder, where we have the electric field still going up like this, but then we also have a dA on the side going that way. and so it's perpendicular. And that way, this will be integral of E dot dA times cosine of pi over 2, which is 0, which makes this whole thing 0. And so that's why I'm ignoring the electric fields on the sides. That's why I'm ignoring the integral of E dot dA along the sides of the cylinder. So the sides, we just ignore them because they equal 0. So this is really a two-part problem, but one part is 0, so we just ignore it. Okay? That kind of makes sense. That has to do with we choose our shape so that the electric field dot dA are either parallel, which is what happens at the top of the cylinder, or they're perpendicular, which is what happens at the sides of the cylinder and therefore can be ignored. Okay, so that's how I justify pulling out the EDA. We'll say the distance is r, but that really doesn't matter because r would just affect the sides of the cylinder, and that's the part we're ignoring. So even though I say it's r, doesn't matter. So then we have electric field times pi r times the area, which is pi r squared. Is for the where this little r is the radius of our circle. But then we also have to take into account, so this is for the top, we also have to take into account the bottom. And you might think that, well, on the bottom, the electric field is going the opposite direction, so we would say, we call it negative. Well, that's true, but the area, the little area vector is also pointing down. So the electric field dot dA will give us the same answer. So this is what I'm going to do here is just going to write 2. So electric field times pi r squared times 2. One for the top, one for the bottom. Okay, so I know there's scribbles everywhere. Let's put it together a little bit. So we got Q enclosed, which is rho pi r squared times h. Rho times pi r squared times h, and now it's all over epsilon naught, equals the electric field, which is an unknown, but we're trying to find it. I'll leave off the vector for now. We're just going for the magnitude, times 2 pi r squared. Okay, so we have an r squareds here. Those conveniently canceled because we weren't very specific about what they were. And solving for E, I'll make this one a vector now. Oh, that's a terrible arrow. Is rho. Oh, the pi's also cancel. Excellent. So I'm always sad to lose pi over 2 epsilon naught. Okay, so let's talk about what this actually means here then. So I'm going to rewrite this briefly without explanation of sigma over 2 epsilon naught. So we have a plane and we're trying to find the electric field at this point. We did it by drawing a Gaussian shape, which was a cylinder. And this is saying that the electric field at this point has to do with the charge density and how thick the plane is. Which is, density is, what is it? Q divided by volume. And volume would be, let's see, width times height times depth. And so when you multiply by the height, you kind of get it canceled out. So what we're kind of looking for is a density along the plane. So like a area density along the plane as opposed to how thick it is. So we could either have a highly charged thin plane or a lightly charged thick plane. And what we'd care is the area going from side to side, and that would give us the strength for the electric field. Divided by 2 epsilon naught. So what's key here then is this is completely independent of how far away you are from the plane, which is kind of counterintuitive. So this is saying that Yep. The electric field strength at this point is the same as the electric field strength at this point. Let's say these are all positives. And at first you're like, wow, that's really counterintuitive. And it is. But what's going on here is, if you look at this point here, let's say you have this point here affecting that point by Coulomb's law, it would be creating electric field that way. This point over here would be creating one going that direction. They're not similar because it's off-centered, but you get the idea here. But everything is going to cancel out except for the vertical component of the electric field. And so as you choose points further and further up, the vertical component from each of these individual discrete points will provide a bigger and bigger contribution. And that bigger contribution cancels out the fact that they are farther away and therefore are going to contribute less. And what happens overall is you get a uniform field in one direction. And so the electric field of a plane is directly related to its surface charge density, and then which is the amount of, for a small amount of Q's for a small amount of area, over 2 epsilon naught. And epsilon naught is of course related to K, where K equals 1 over 4 pi. Oh, it looks like a 9, it's supposed to be a 4. Pi epsilon naught. Yep. So a couple of small things. So you'll normally see it written in terms of sigma and not in terms of a volumetric density. So don't be thrown off by that. And this is why whenever I see a problem and something is said along the lines of there's a uniform electric field from left to right, I will immediately draw up parallel plate capacitors, because two parallel plates, relatively infinite, of plane charges, and the idea is that would give you a uniform electric field in this direction. And it's easier for me to visualize then with the two infinite planes and see how it would repel or attract charges than just the conceptual idea of uniform electric field. So the idea is you have a positive charge here. It's like, well, okay, it's obviously going to be repelled by the positives and attracted by the negatives, and therefore it'll move to the right. And that's why the Gauss's law explains here, or at least proves, maybe not explains, but proves why infinite planes produce a uniform electric field regardless of how far away you are from them. Now, one other item of note, I guess some tricks to be watching out for in life. So just like we had with the sphere, if it's a conductor, you have to be careful of taking a electric field with inside a conductor. Similar concept here. So if you have let's say you have a large charged plate, large meaning as far as you're concerned it's infinite, and you have a bunch of charges on it, and it has, let's say you're told that it has a surface charge density, sigma, which would be a small amount of charge for a small amount of area of sigma. And they want you to find the electric field. So what you would necessarily think is, okay, so we're going to be dealing with Gauss's law, which would be Q enclosed over epsilon naught equals double integral E dot dA. But you have memorized that, all right, for an infinite plane, we have sigma over 2 epsilon naught. So you just know, because it should be memorized. You should probably memorize a sphere and a plane, and also an infinite line charge, which we'll get to next time. You know that you have sigma over 2 epsilon naught equals the electric field. Well, that's true, it does, But when you're talking about when they give you a surface charge density, they're probably talking about the surface of the conductor. And you have to read the question to be careful. So what you really have here is you have two surfaces with charge on them. You have this surface and that surface. So if you're given a total amount of Q on the plane, then you'd be like, okay, Q enclosed, sigma over 2 epsilon naught equals the electric field. But if they say the surface charge density of this infinite plane is sigma, then what you're dealing with is not one plane, but two planes. So what happens is you have the electric field from these charges, then you have the electric field added on to the charges below. And so what you'll get then is the electric field equals sigma over epsilon, because it's divided by 2, multiplied by 2, they cancel out, get 1. And so that is one thing to be careful of, is if they say a conductor with a surface charge density, you might have to double your answer, because you're not really talking about one plane. It's as if you're talking about two planes of electrical charges, one on top of each other. And then they reinforce each other through superposition. And that's because in a conductor, all the charges are going to migrate to all the excess charges are going to migrate to the outer outer surface area of your shape. Okay, so that covers the first part of Gauss's law. We'll talk about cylinders and line charges next. So the big takeaways here are, so we have Gauss's law right here. Q enclosed over epsilon naught equals double integral E dot dA. And then for a sphere, we're going to get Coulomb. If we do this over a sphere charge, we're going to get Coulomb's law. So we'll get electric field equals K, should probably do A. Nah, not going to worry about it. Okay. We get K, way sideways. KQ over R squared, where this is the enclosed charge. And then for a plane, a single plane of electric, make a little A area just for the direction. For the magnitude of a plane charge, we're going to get sigma, which is the for a small amount of charge, dq, d area, so it's the surface charge density over 2 epsilon naught. Okay? And if you don't have access to epsilon naught, you can then find epsilon naught through K, which you'll probably get, Coulomb's constant, 1 over 4 pi epsilon naught. Okay, and then next time we'll go over cylinders and infinite line charges. Thanks.